Welcome to our video on solving a culvert design problem involving hydraulic calculations. Let's tackle this step by step. Here's our problem. A 25-inch diameter, 2-meter long culvert has been designed to carry a maximum discharge of 700 liters per second when flowing half full. Its roughness coefficient is 0.015. If the inlet and outlet are both unsubmerged, the difference in elevation between the inlet and the outlet should be, and we're given four options: A, 5 centimeters, B, 7.5 centimeters, C, 10 centimeters, and D, 12.5 centimeters. To solve this problem, we first need to convert all values to consistent units. Since we're working with hydraulic calculations, we'll use the International System of Units, or SI units. First, let's convert the culvert diameter from inches to meters. 25 inches multiplied by 25.4 millimeters per inch gives us 635 millimeters, which is 0.635 meters. The flow rate of 700 liters per second is equivalent to 0.7 cubic meters per second. The culvert length is already given as 2 meters, and the Manning's roughness coefficient of 0.015 is already dimensionless, so no conversion is needed there. Let's now understand the geometry of our half-full circular culvert. Since water is flowing through half of the culvert, we need to determine the hydraulic parameters for this condition. The wetted area, A, for a half-full circular conduit, is 1/2 of the full circular area. So the area equals pi times d squared divided by 8. The wetted perimeter, P, is half the circumference of the circle, which equals pi times d divided by 2. From these, we can compute the hydraulic radius, R, which equals the wetted area divided by the wetted perimeter. Simplifying this, we get R equals d divided by 4. Now, let's compute the numerical values of the wetted area and the hydraulic radius. Substituting d equals 0.635 meters into our area formula, we get A equals pi times 0.635 squared divided by 8, which gives us approximately 0.1584 square meters. Similarly, for the hydraulic radius, R equals 0.635 divided by 4, which equals 0.15875 meters. Now, we'll use Manning's equation to find the slope of the culvert. Manning's equation is a fundamental formula in open channel flow calculations. The equation states that the flow rate, Q, equals 1 over n times a times r to the power of 2/3 times s to the power of 1/2. We need to solve for s, the slope. Rearranging the equation, we get south equals the square of q times n divided by a times r to the power of 2/3. First, let's calculate r to the power of 2/3. R to the power of 2/3 equals 0.15875 to the power of 2/3, which is approximately 0.2934. Now, substituting all our values, south equals the square of 0.700 times 0.015 divided by 0.1584 times 0.2934. This gives us south equals the square of approximately 0.2258, which equals about 0.0510. Next, we need to calculate the head loss over the culvert length. Head loss, H_F, equals the slope s times the length L. So, H_F equals 0.0510 times 2 meters, which is approximately 0.102 meters or 10.2 centimeters. Since both the inlet and outlet are unsubmerged, the elevation difference between them must accommodate the full head loss we just calculated. Here's a visualization of the culvert with the inlet and outlet. The elevation difference needs to be about 10 centimeters to allow for the calculated head loss. Therefore, the answer is C, 10 centimeters. Let's summarize the steps we followed to solve this problem. First, we converted all values to SI units. Second, we determined the geometric properties of the half-full circular culvert. Third, we calculated the wetted area and hydraulic radius. Fourth, we applied Manning's equation to find the slope required for the given flow rate. Fifth, we calculated the head loss over the culvert length. Finally, we determined that the required elevation difference is 10 centimeters. This example illustrates how hydraulic engineering principles are applied to design culverts that can efficiently handle specified flow rates.